Yes, I will.
Shall we start?
For now, because it's like an open door, there's a door to reality. I try to. Maybe after I will go to yes, of course. It's funny.
Okay, so let us start. So, yes. Okay, so welcome to the afternoon session on biophysics. So the first speaker is Arkady Pikowski from University of Potsdam. Please, Arkady.
So thank you. And so this is a collaboration of research with Lev Zimring from this from Santiago. So the fact paper was been published a little bit earlier, but it is attributed to April 23. And so I will try to explain what is this asymmetric damage segregation and cell populations. But let me first show this photo showing me and here. And it was taken 7 years ago. So you see there are some changes. And altogether, these changes in our life, so we describe as aging. There is also some statistical mechanics, some notion of aging, but here it is a pure biological sense. So it's human beings so go this way from the birth to the death. But at some stage, so people can child, and so the whole population remains, although every individual has some, to say, finite span of their life. Yeah? And as a population, it produces healthy offspring, and all the, how to say, illnesses are going with aging until death. Yes. But there are not all organisms are like this. So there are on a very elementary level, if we are speaking about cells. So there is no real notion of aging, because as a cell divides, so there are 2 new cells, and they are newborn, and so to say, each of them is young, and they continue. They continue in this manner, and the population of cells develops in number, and there are only young cells there. So it's the main process is that mother cell divides into 2 daughter cells, and they are identical genetically. So we can assume some neglect of mutations. And so there is a number of identically, genetically identical elementary organisms. So I took from Wikipedia this number, so that now there is a huge number, larger than the number of neurons in the brain. And so in this respect, so this term global cell population refers to this group of genetically identical cells. So there is no any genetic difference this says that they are really absolutely identical, like this synchronized dynamical systems. You have two copies of one system and synchronize them, they are exactly the same. The answer is not. So there is some variability inside such a population, which is often termed as non-genetical or phenotypic variability. And also, it not interests also not a biological community, but for physicists, by physicists. And so I took these two pictures from this review article, non-genetic variability in microbial populations, published in report Progress in Physics. So this is also interesting for physicists. So one can look at these seemingly identical cells and see so that the growth rate, so the property are not, it's not a delta function, but there is some distribution of their properties. And there is a division rate, which essentially means so that their lifetime. The lifetime has also certain distribution, so they live different times. And so the idea why this happens is the following. So that in the cell, biomolecules become damaged. And the number of these damaged biomolecules so somehow influences the properties of the cell. And so the idea is also that this damage, which is considered as some kind of real number, which characterizes the cell, it's distributed between daughters, but this distribution is not equal. So that not 50-50, but there is some portion which one daughter inherits and some portion which another daughter inherits. And this makes these two daughters non-identical, although they have identical genes. So in this picture, so there is I found this picture from this paper, it illustrates, but it is some kind of totally asymmetric segregation. So that you have these damaged molecules, and during division, one cell inherits everything and another inherits zero, but this is extreme case. So one could imagine that there is something closer to 50-50, but not exactly. Maybe one cell inherits 60%, another 40%, and then it makes their properties different. So this is how you can imagine this biological process. And now we want to build a mathematical model to follow this and to describe this. And we have in this model to take into account three important ingredients. I will first speak about damage gain. So during the lifetime of a cell, damage increases. And you can imagine in the literature we have found different equations how these people model this process. So there could be a growth by a fixed amount. So independently of lifetime, each cell adds some number of biomolecules to it. Or it could be a linear in time growth, so that means the total addition will be proportional to the lifetime. Or you can write for this damage, which is a scalar quantity, positive quantity, some kind of linear differential equation for it, so that you have something like x dollar is equal to some coefficient multiplied by x plus something. So it will be then a solution of such a simple equation. Say it will be so that there is some autocatalytic production degradation. It will be some at the end some function of initial state at one time, but not maybe little bit complex. Okay. Now about lifetime. You can, in the simplest case, imagine that there is a lifetime is damage independent. The more, how to say, realistic is so that the cells with larger damage, they live longer. It means so it's not good for cells because so you want to divide earlier, the better the earlier you divide. So it is a that cell lives longer, but it means so then its division is postponed. Or some people suggested models, something like integrate and divide. So you integrate some, you write some equation for some growing quantity, and when this quantity reaches the maximum, you divide, and when you reach a threshold. Okay, and then so this process happens as an instant. The division, how you redistribute your damage between two daughters. You have daughter 1 and daughter 2, and the one function could be just a linear one, so that one daughter gets some portion, and another gets the rest, and A some constant which says about perceiving. Or there could be some nonlinear distribution functions. Now, in all models here refer to some deterministic assumption. Maybe it is not good for real cells where you are we can discuss how to include also probabilities in this, because you can imagine that each of these can be also formulated in some probabilistic manner. Okay, so let us look at the simplest case where you have a linear damage redistribution and constant lifetimes, and you add constant amount of damage during the lifetime. And this means so that if you look at two daughters at the moment when they are born, so that the damage of their mother when it was born is related with symmetry comes because they are different. And if you draw this relation so that you have two linear functions, so they're here, and this means so that you can simply say, okay, given any damage at the mother generation, I have two daughters according to these 2 points here, and this will be the next damage, and I have to continue. Now, it's in this particular case, it is sum is 1, so there is no gap here in these linear functions. But in different models, you can have these functions with gap and functions with overlap. Now, in fact, so this equation is rather known in the not maybe in the standard theory of dynamical systems, but there is a mathematical object which is called iterated function system. It was created, it was invented in some sense to create fractals. So you take some set and you make different linear functions So this is how it looks like if you just model what simple equations. So this time is a generation, so they're constant times. And there are two, you start with just one cell, you generate two, again it will be 4, and so on. The number grows. And if you look at this moment or some moment of time, 10 and 15, how many cells have reached damage? You draw the probability distribution function, and you see it has peaks. It is a fractal distribution, of course. So these peaks will eventually become infinite, but it is just a fractal measure. Now, it's a little bit more complex if you have non-constant lifetimes. So that means that, for example, in this picture, the moments of when you give birth, so a different generations, they are somehow mixed. Yeah, you see colors here are mixed because some live longer, some live shorter, but nevertheless, you get also a fractal like here, the same iterative function system, but the events are not synchronous in time, but somehow mixed. Now, it is, if you think about something like dynamical system, so the natural question is how correlated are these damages in different generations. Now, if you go forward in time, so each cell has two daughters, you cannot have a trajectory. But if you move backward in time, so each cell has a unique set of cells of their ancestors. Or no, ancestors. Yeah? So it means so that we have a trajectory, we can make an average, and so this is this trajectory back in time, and you see it looks rather irregular, and correlation function decreases, and indeed, so if you now revert this picture of iterative function systems and put time here, previous time, we see so that it will be just a chaotic map. So it is a skewed Bernoulli map, which says you that if you go back in time, so you have criticity, and this explains this loss of correlations. Now, it is a simple exercise. I said about fractals, so you can calculate fractal dimension. It's just the same formulas which you know from the multi-fractal formalism in books about chaos. Now, of course, so that's, if this A and B larger than 1, you cannot do this. Because so these two functions overlap and you don't get a dynamical system. You still can calculate fractal properties, but there is no corresponding dynamical system. So it is for me, it is a challenge, so how to relate it to a dynamical system. But from the viewpoint of the measure, it is okay. Now, you can, now the question is, are these fractal properties generic or not? And the answer is yes, so it is, even if you use nonlinear functions, that still it will be a typical fractal. So here, in this, so here, for example, two nonlinear functions, how inheritance work, and here it is a probability density, and with red it is an integrated probability density, which looks like a devil staircase. But in some cases, with strong overlap, it looks really like a smooth curve. The one can argues that this goes to Gaussian. But in many other cases, whatever you take, you get a fractal structure. Now, so one can think so how you can derive, system, not at the birth time, but if you look at population at any time. And our idea was to use a description similar to what one uses for oscillators, and in fact, so what in previous talk by Olmi and the next talk of Alessandro Taccini, probably similar kinetic equations are used. So you can imagine that cell is like oscillating. It starts with phase 0, ends with phase 1, phase grows, and instead of the neurons, they produce a spike, and then they start again. Here, it's cell divides into two, and then these two start again. Now, in this kinetic equation, the number of cells grows. And if you want to have a stationary solution, you need to impose some death. So you have to remove cells from this population, otherwise they will go definitely. And so you induce a death term here, which makes it, but this term is not told in advance, so it is some kind of multiplier of the problem. So it says you how fast your population is growing, and you impose the corresponding death term to find. And so you can work with this kinetic equation. You have a condition how the damage is redistributed at the end of the beginning. So this death rate is coming here as a solution of this equation. And okay, I'll maybe skip some things. So okay, so now if you look not at the probability distribution at the birth time you have a fractal. But if you just look on your population of cells, so that some are just born and some are maybe close to the next division, and damage grows, so there is a mixture of everything. So you get some convolution integral of your fractal density. So at the end, it is not fractal, but has some peaks. So the density stationary of all ages, it gives such a non-fractal, but also not smooth property. And interesting thing from biological point of view that this diversity of damages and diversity of how it is inherited, it improves this parameter gamma. So if you have diversity, your population as a whole grows faster than without it. So if you have dependence of the time, of the lifetime, on the damage, and if you have diversity, you always have growth of this parameter gamma, which say, yeah, so that this is beneficial for the population to redistribute damage and not improve there. Now, in fact, so I hear about stochastic evolution. So you replace these deterministic functions by some densities. You can also put this into kinetic equation. And of course, so with this smooth densities, transition probabilities, you lose this fractal structure, but nevertheless you can use this kinetic description to find distribution of the damage in the cells. So my conclusions is so that there is a rather simple but interesting example how you can apply these ideas from the dynamical system to this problem of damage segregation. And so you get easily fractal things, so maybe they are hardly observable in the real cells. But there is a possibility to use kinetic equation, which is essentially conservation of probability, to have a statistical description, and this equation gives you the asymmetry damage. faster growth of the population. Thank you.
Thank you very much for this interesting presentation. Are there any questions? I have a curiosity meanwhile. So, can you learn something about this multifractal spectrum that you can extract from this this model? So, or is it? I mean,
So there is a so this type of iterative function system. So they were considered by some physicists some maybe 20 years, more than 20 years ago. Ray Capra worked on this, and he was puzzled with some fractal structure. Now, there's exactly recent years there was a lot of progress in mathematical literature because mathematicians try to prove different fractal properties of these iterative function systems. Especially difficult is the situation with overlap. Because without overlap, you have the simple formulas for multifactor. With overlap, it was not clear just recent years, so there now works about, so that very seemingly there is a phase transition in the multifactor formalism. But this is, I would say, also a problem because you hardly expect for real biological system such as a deterministic rule, but it is really for mathematical and physicists interested in fractals, it is still not clear so what are multifractal properties. So there are indications that there is a phase transition in this multifractality.
okay.
One short
Yes.
question. Like, I think we're close enough, but thank you. Yeah, okay, sure. I know that this is the worstest question to the scientist, but how you can see the way to use this as a functionality in the future? Like how to use the research as a functional functionality, like how it can be used in a medicine or in any other field of study.
What I can mention that one could try maybe due to some visualization of these damages, try to really get information about distribution of damage and try to fit this functions which you assume so that lifetime is somehow related to the damage. So you can potentially experiment for each cell. You can imagine a lifetime if you can also visualize the damage maybe in the beginning and the end in some way. You can try to find some relations and so this is this situation may potentially be an even control. But this is the global community, and it looks like it is relatively universal.
Other question? Yes.
Just about this, is there any experimental confirmation of this fractal distribution?
No, about fractal, definitely not. So there are some indications that there is a distribution. But you see, so if I look, what deterministic will do? Because we will use this deterministic models as the simplest one. And they have interesting properties. But of course, so this variety is there by
Because I remember that, for instance, when you start to synchronize the verification, and then you have this, as you said, spreading of the verification time, which can sometimes be used.
I'm not sure, but might be in the spirit of one of previous talks about social effects. So if inheritance of wealth is going in similar ways, so that you inherit, so different siblings so carry different parts of their wealth, and they increase it and gain, so then there will be maybe peaks, very rich and very poor, and nobody in the middle which will resemble totality. Might be.
Okay. So next, yeah, next speaker is Alessandro Torcini from University of Sergi. Please.
Thanks for the invitation, and I will present a work. We are speaking about neurons, in particular networks of psychic neurons, and of
Thank you very much. Questions? So I have a curiosity. So you mentioned at the end the limitations on the noise. So, but if you compare this, the quenched noise with the external noise, so are there, should they be the same order, or so should they? What is the typical?
Okay. For the quenched, allora, for this theory to work, to have a low dimensional reduction, you need to assume that the quenched disorder is distributed as a Lorentzian. This is a strong limitation if you want. Otherwise, you cannot perform the integrals and you remain with an n-dimensional system. For the amplitude of the noise, if you have, you can once more to make everything. So it's all closed if you want. It's completely closed. With Gaussian noise, you can, as we have done, you can write, or also as Arcadi has done with a different approach, you can write a hierarchy of equation that is not closed.
Okay.
So an infinity hierarchy that you can truncate. The amplitude, we try to give an estimation, but we give an estimation, but I don't believe too much. So it depends on the cases. I have not a recipe to say you when it will work or not. That's one of the main problems.
Okay.
If there's an experimental indication of the real distribution.
For sure. We are not Lorentzian. Okay, by the way. Okay. If this is the question, no, if you want other, let's say, they are not. So you know, the biology, no? And then let's say they are distributed. So a Lorentzian has a long tail that you have some problem. But for example, in all what I have shown you, at a certain point, I assume that the distribution of the integers was Lorentzian. I wrote it somewhere here. If you think one moment, it makes no sense because negative value of the integers I cannot do. So I truncated. So we have truncated and still in the simulation of the network. And so it still works to a large extent. So you can manage.
Other questions? Okay, if no, let's thank the speaker again.